I think we're going to begin the second session. Brilliant. Thank you very much. So this is first of all, thanks very much to Baz and the gang for the first session, really interesting. The second session is the G3 theme, which is the Geohazards, Georesilience and Geoengineering, or in some sequence. I always get a bit confused. My name's Matt. I'm the G3 theme lead at the Geological Society and the UK Geophysical lead at Global Maritime. G3, I think, runs through all of geosciences, really. So we've got significant overlap, I think, with the energy transition. But as the climate's transitioning, as society is transitioning, we've got the need for significant infrastructure projects in which we need to prepare for, mitigate, and respond to geohazards. That's via engineering and also by embedding that resilience into our systems. We've got three really inspirational early career speakers today, which I'm really happy to have had volunteers to come and speak today. We've got Claire Chemonsky, who's principal geomorphologist at Jacobs. Millie Happenden, who's an engineering geologist at Global Maritime, and Georgie Harbottle, who's a geotechnical project engineer at SSER. So with no further ado, I'll pass over to you, Claire, if you'd like to come up.
Okay. Just check this. Yeah, okay, it works. Cool. Welcome everyone. A little slight change in gears here. So today I'm going to actually be presenting about what I do as a engineering geomorphologist, and then present a case study of the work I've been doing on the Isle of Wight in relation to landslide hazard. So just for starters, so what is an engineering geomorphologist? So before I dive into that, I'm going to start off by explaining when I started university, I didn't really know much about geomorphology anyway, let alone engineering geomorphologist as a career. So during my undergraduate, I actually did an undergraduate in physical geography, so quite different to, I imagine, many of you here today. So I did that at Sussex University, and through that, I learned a lot about geomorphology in terms of the landforms and the processes that shape them. And that really inspired me. I was like, this is really interesting, especially in relation to geohazards, so, extreme events, things like that, and the impact it has on people, especially. So beyond that, I thought, well, I want to do this. This is kind of what I'm interested in, but is there really, like, what can I do? Was there a career? But thankfully, I think I was just very lucky. I had a very good lecturer who suggested that I did an MSc in engineering geomorphology, which was an applied course. So you essentially learn, obviously, the theoretical basis in geomorphology, but also how you apply this in an engineering sense. So this kind of brings us to this slide here. So what is an engineering geomorphologist? So essentially, we are geoscience specialists who apply geomorphological knowledge and skills to engineering and infrastructure projects. So essentially, we kind of bridge the gap in between the earth sciences and civil and engineering projects. And importantly, in the applied sense, we are involved in solving real-world issues. So this is ensuring that developments are not only safe, sustainable, but also resilient to natural hazards. I know I'm talking about the Isle of Wight today, but I thought this was a really good image to illustrate where geomorphologists really come into their own interacting. So we're looking at a debris flow hazard in the Highlands of Scotland. So this is one of the projects that I'm working on, and we've got a number of projects actually up there where we've been doing debris flow hazard assessments. And the reason why we're brought in is because, if a debris flow hazard happens where there's nobody around, nobody really cares. But this particular slide, this is in 2020, impacted one of the main A roads into the Highlands and actually caused the road to be closed for a significant amount of time. Thankfully, nobody was hurt, but it just shows the impact that natural hazards can have on people and also assets. So there's a few snaps here. So what do we do and why do we do it? So I think both questions, at least for me, they're pretty much intertwined. So as an engineering geomorphologist, we get to work in a range of environments. This might range all the way from, as I am, in the Isle of Wight or coast, it might be in quaternary environments where you've got quaternary deposits, you've got special landforms develop in those areas. We've also got mountain environments, which I work quite a bit in, and also, you know, rivers. I think that's kind of one of my main areas of interest. But also there are a range of engineering problems or issues that we might be called in on. So some of the projects we work on are like large linear infrastructure projects. We might be working on sort of, say, for example, pipelines. I'll talk about this again later, but also we also look at submarine geomorphology as well, in particular when it relates to interconnected cables. And also my colleague there, Alex, he actually specialises in peat landslide hazard assessment. So that in relation to your slides earlier, Gemma, he actually works on quite a few of the wind farm projects, ensuring that they're built on unstable ground. So just on the second point there, graduates take on a range of projects. So this Anya and Natalie, they're our latest graduates. They joined about a year ago. So we kind of throw them in the deep end, and says they can go into any environment really, any project. And a lot of what we do, I think I might be jumping ahead again. They kind of, you know, you kind of learn a lot on site. You don't learn everything in a lecture theatre about how to do a geomorphological assessment. You have to be out there in the field looking at these landforms and to understand the processes that are at play. And also, I just threw that on the bottom there. Something I really enjoy about the work I do is the fact that it's not prescriptive. It's not like filling out, you don't have to go through a checklist or anything. There's a set skill and knowledge base that you have, but then you're able to apply that and develop bespoke assessments for the particular engineering problem that's at hand. And I've said here also innovation that allows us to be innovative with the kind of solutions that we come up with, and we can use different you know, data sets that are coming, you know, everything's kind of moving, technology is moving really fast right now, so we're kind of learning as we go. And also bringing in new graduates, they bring in some really, you know, their own unique skill sets they've learned at university. So I think it kind of leads us nicely onto the point about teamwork and collaboration. Yeah, we all kind of bring our own skills together, and we can collaborate in the field together. But not only that, obviously, as you're probably aware, geomorphology, it kind of sits in amongst all the other disciplines. So it's very interdisciplinary in terms of, you know, who you might be working with on a daily basis. So I work with hydrogeologists, engineering geologists, and even ecologists, you know, everybody. Just on the point of public and professional engagement, I've already spoken to a couple of you earlier about, we do quite a lot with, especially with the Geological Society field trips, where we go out into the field and bring not only the public, but also professionals like yourselves into the field and have a look at some of the geomorphological issues that we're kind of currently facing. So these couple of pictures here, these are from September this year. We went out into the field down in Dorset to have a look at some of the coastal landslides there. Making a difference, again, I've kind of already sort of spoken about that. So in terms of, you know, when it comes to solution finding, that's the word I was trying to look for, solution finding, and essentially making a difference to communities and property owners. And then finally, I put this on as a little bit of a joke, ice cream, because of the photograph, but actually it's kind of important in the sense that, for me at least, I have a lot of fun with what I do in geomorphology. I really enjoy being out learning on site and also teaching and you know, just working with my colleagues. It's a lot of fun. So yeah, so this is the case study. So I just want to introduce you to the Isle of Wight. I'm going to run through this very quickly, so I'm sorry if I fly through. You can feel free to ask questions later. So I'm just going to introduce the Undercliff, which is a site I've been working on for a number of years now. I'll talk about our role as geomorphologists on this project, how we went about building the ground model and landslide risk management, and a couple of concluding remarks. So the Undercliff is actually the largest onshore landslide complex in Northwest Europe. So it's essentially a progressive deep-seated ground movement. So there's been a long history of ground movements. These are some of the pictures from along the undercliff in this time period. So annually, this results in about £3 million worth of damage every year. So given this, it's got a long history. There's been lots of extensive investigations since the 1980s. And there's been lots of engineering to stabilise and deal with this issue. Though in recent years, there's been a bit of change. So you might remember a couple of years ago, there were two significant slides in the Isle of Wight. This was at Bonchurch on the left there, and also St Lawrence. You can see the scale of these landslides. So they were really quite devastating for the people that lived there. You can see that this is one of the main artery roads down to the south of the island. And essentially they had to close the road for an extended period of time because they didn't know, what's the landslide going to do next? Is it safe to drive there? And also these properties in St Lawrence, this one is literally rafted on a landslide block, and is sliding down slopes. So obviously, these houses are lost to these people, and they're essentially, it's not a very good situation. And we'll see later that it's not just everything that's in the active side. You've got to consider everything around it. So this brings us to our second point. So there's residual uncertainties that exist in predicting landslide response, particularly in light of future climate change, but also in communicating hazard and risks to the public. So improving our understanding of the site is pretty much key, and that's what we do as geomorphologists. So just to give you a high level kind of impression of what we do. So obviously, as you're aware, geomorphology is about understanding the system and the process that control them. And the way we do that is to build a ground model. So we have, you might have come across all this before, but I'll go through it anyway. So we've got our desk review, so that's all the available information, site reconnaissance or field work, geomorphological mapping, and monitoring and data collection. So this all goes, this is like a constantly evolving model. So as new information comes in, we're constantly updating it. And this will go into hazard mapping and risk assessment. And then in turn, that will inform our landslide risk management strategy and the development of engineering solutions. So I'll run through this as quickly as possible. So ground model, first things, we've got topographic data and borehole records. So just a quick run through. Essentially, we've got a sandwich here. We've got a gold clay sandwich. We've got gold clay there, and then upper green sand and lower green sand there. So that's kind of what we're looking at in terms of the geomorphology, the geology. And then our chalk on top. So essentially the landslide is then kind of, the slope is like draped by this upper green sand debris. Just to highlight there, we've got these confined aquifers, unconfined up there, and these are the shear surfaces that are known shear surfaces that are developed in the bottom of the gold clay and in the sand rock. So using that information, I had developed a 3D ground model, essentially, which modelled what's known as the St Lawrence incline. So that's kind of like, as you can see there, it's modelling that surface of one of the shear zones. So this is really important because it controls where the strata outcrop at the shoreline, and it also affects the hydrogeology in terms of the flow direction and gradient. So this is a cross section through. So this is like looking from one end of the undercliff to the other. This enables us to identify where the shear surfaces are in relation to sea level. And this is important because it affects the spatial distribution of ground instability in terms of the mechanisms and depth. So here we've got our shear surfaces labelled here. So in the middle here, we've got these shear surfaces that are close to or below sea level. So as a result, we tend to see these deeper seated failures, particularly where the hydrostatic pressures are increased. And we tend to see mudslides and rockfall on the kind of distal ends of the undercliff. So our site, St Lawrence and Bonchurch. St Lawrence is in this area where we have these deeper seated shears. And in Bonchurch, they're higher up in the cliff, and the cliffs are formed of this softer sand rock. So quickly to run through, we've got additional things we want to add. So we've got our geomorphological mapping, we've got records of previous instability, and we've got our instrumentation. So this is piezometers, inclinometers, ground movement markers, and laser scanning. So this is a geomorphological map for the whole of the undercliff. which is kind of handy. This was actually produced back in the 90s, but it provides us a really good basis for developing our ground model. I won't go into the detail right now because not enough time. And then ground monitoring and past records. So here we have some laser scanning data, which is really helpful in terms of understanding movement in the undercliff. And again, ground movement markers that are manually, the information is manually collected. That also gives us an indication of where movements on particular landslide blocks is occurring. And also I've added here rainfall and historical events record, because this is really important where particularly if we're looking at the influence of climate change, and we're actually able to put together this record, which actually suggests, this is on an early presentation I did at the Geological Society, that indicate that actually rainfall is an important, probably the most important driver in stability in the undercliff alongside coastal erosion. And what we can see actually is that the number of events seem to be increasing along with increasing intensity and prolonged rainfall. So ultimately we end up with these block models. Again, I probably won't go into too much detail, but essentially this is St. Lawrence up here, this deep-seated shear surface here, but where we have actually seen the movement is up in the upper tier in the Gault clay. So as I said here, this is primarily driven by rainfall up in the top of the cliff here. And we have this kind of debris apron, which essentially provides toe support for the rest of the landslide. And then Bonchurch, we have these kind of still fairly deep rotational slides, but they're not, the shear surface is way above the cliff line. And again, what we found is that at Bonchurch, we seem to have coastal erosion plays an equally important part. And this is probably what I find the most interesting part, is the geomorph mapping. So going out in the field, doing site work, seeing what you can't see in the geodigital data. So this is some geomorphological mapping that we've done for St. Lawrence, just to highlight again this upper tier landslide in the Gault clay, and the degradation. Essentially the slope is unraveling from west to east. So we're kind of in this active zone now, but you know, it could be in the future this area also begins to unravel. And then again, Bonchurch, as I mentioned, this is a DTM difference map, so elevation difference essentially, and it shows prior to that big landslide, we actually had a focus of a coastal erosion there, which we believe is the trigger, one of the main triggers, but also, of course, as I mentioned, rainfall. So if I bring up the next slide, that's our geomorph mapping for the Bonchurch failure. And helpfully, on the next slide, just to show you some drone imagery that was collected. So in some areas, so for the Bonchurch landslide, we can't go onto that landslide, it's simply too dangerous apart from walking around the edges. So that's where drone imagery is really becoming very useful for us in terms of having a look at this is pictures of the backscarp. We can have a look at the condition. We see these kind of big joints opening up. So we can't see that obviously just walking around. Finally, I just want to touch on landslide risk management. So this is, okay, we know this, what do we do about it? I think essentially we have what do we do and then what we seek to achieve here. So ultimately we want to avoid the risk, reduce the vulnerability, reduce the likelihood of the geohazard, and also improve risk awareness. So I'm just going to go through a couple extremely briefly. So in terms of monitoring, it's really all about community safety and assurance. And the way we do that is to provide an evidence base through scientific investigation, as I've already mentioned, all the monitoring data which feeds into our ground model. And at Jacobs, obviously, this is part of the essential thing of what we do is they bring together all this information for integrated analysis. So at Bonchurch, for example, this allowed us to develop an early warning system based on rainfall intensities. Planning controls, again, we can develop hazard maps and risk maps to provide guidance for the local authorities and planners and also the residents. And it's also a really helpful way of communicating risk, and also along with the block models to communicate risk to the public, because it's not an easy thing to understand when you've got loads of numbers being thrown at you. And then quantitative risk assessment is something we also do in terms of assessing, you know, what areas could actually do with, you know, looking at engineering measures and doing cost benefit analysis for that. Second to last slide, engineering measures. So along the undercliff, there's significant investment and active management of the undercliff. So this might be in terms of maintaining or improving the standing protection of coastal defences and also deep drainage. So that links back to what I was talking about, those deep-seated shear surfaces that interact with those confined aquifers there. And also investigation of options. This is where we come into it. Emergency response. So this is the Eastern Esplanade of Ventnor. I was down here a couple of years ago supporting the ground investigation with the ground model. So we know what we're finding at depth essentially. And also we support design through the ground model that we've developed. Concluding remarks, it's more questions. So these are the questions I'd like to ask you. Are you fascinated by natural processes and geohazards? Are you interested in technically challenging work? Or are you interested in finding solutions for communities and assets owners? And also, would you like to make a difference? So if that is the case, then consider a career in geomorphology. And that is all. Thank you very much.
We may have time for a quick question if anyone has one.
How long have you spent on each project? Okay, so that's a very good question. It depends on the scale of the project. So largely in the infrastructure projects, you can be in there from the beginning of the life cycle of the project to the end. And obviously, as you're aware, they take years. And then I also work on private small scale kind of slope stabilization assessments. And again, I go there for the day. I do my assessment in the office and it's wrapped up within about a week. So it really varies.
Thanks so much.
No worries.
And we can take more take more questions after the sort of session. I've also just been reminded to encourage you guys to sort of sign up for the other workshops when we complete here. But we've got 2 more speakers. And thanks, Claire, for introducing ground models in that talk there. And I think Millie will be talking about conceptual ground models in the offshore setting.
Yes. Cool. Hi, everyone. I'm Millie, and I'm an engineering geologist at Global Maritime. And I'll be talking about conceptual ground modelling for floating offshore wind using the case study, the MA17 project. Before I start, I wanted to give a bit of a background of my career to date. So I graduated from the University of Southampton in 2021, an integrated master's in geology. And then for the first 2 years of my career, I was a geotechnical / geoenvironmental engineer for an onshore consultancy called LEAP, which mainly deal with undertaking ground investigation for house builders. And then after that, I wanted to be more technically challenged. So I made that transition offshore to Global Maritime, where I currently work. So this slide just gives you a bit of background as to my day-to-day job and what a typical project life cycle looks like in a simplified form, just to give you an idea. So firstly, once we receive a project, you typically undertake a desktop study, which involves researching the site, looking up on the internet and scientific literature and geological maps to find out what the expected geological formations are, potential geohazards that could be present at the site. And this can be visually conceptualized, such as this cross-section here. The next kind of stage would be to design and manage site investigation or ground investigation, which would involve mobilizing an offshore vessel to the site and drilling boreholes or undertaking in situ testing, such as CPTs, to kind of collect and analyse data about the site's ground conditions. This data is then collated and an observational ground model is created, which is an easy visual communication tool to understand what's going on a site-wide scale. And then lastly, you typically group soils in terms of similar lithology or similar geotechnical properties, otherwise known as an engineering geological unit. And for each engineering geological unit, you would create geotechnical design parameters, which can then be used to inform turbine foundation design. So now we're talking about floating offshore wind, which is the main theme of my presentation. So why is offshore wind, floating offshore wind, the future? So currently, fixed offshore wind is well established in UK waters, especially the North Sea, with many planned and operational wind farms. However, there are limitations to fixed offshore wind in that it is difficult to install fixed wind turbines beyond 60 metres water depth, becomes commercially unviable and quite technically challenging. And here's some examples of fixed offshore wind types. You can either have like a monopile, which is directly attached to the seabed, or like a jacket substructure. But with floating offshore wind, it can overcome these limitations in that it can be installed in water depths greater than 60 metres. And this, because of this, it can open up vast new areas offshore, which have an even greater wind resource, not to mention the risks of impacts on other ocean users are much lower further offshore, and the contribution to net zero targets. Currently, floating offshore wind is very new and innovative, and there are currently no commercial scale floating offshore wind farms in UK waters. However, this is set to change in the coming years. So now I'm going to be talking about the site investigation challenges with respect to floating offshore wind, because it differs from your conventional fixed approach. First challenge is that with a floating offshore wind farm, so there's quite a large footprint you can see here, where the anchor locations can be up to 1 kilometre apart, and that's quite different from a jacket substructure, which is about 30 by 30 metres squared typically. So because of this larger footprint, for floating offshore wind turbines, there's a potential for higher geological complexity and geological heterogeneity over this footprint than typical for a fixed offshore wind. So the site investigation needs to capture this geological complexity, which is going to have cost implications associated with it. The second challenge is about scaling. So there's a significant change in the numbers of individual foundations relative to fixed offshore wind. So for example, for a fixed monopile, 60 number wind turbine site, current best practice says that you need approximately 1 exploratory hole per wind turbine. So that would mean about 60 exploratory holes that would need to be undertaken as part of a ground investigation. In comparison, for a floating 6-line mooring system, if you've got 6 anchors per wind turbine, there's a huge upscale in the number of exploratory holes that you would need, up to 3 to 6 times more, which is very expensive and time consuming, and developers want to limit their costs. So that is quite a big challenge for us to try and solve. So these challenges highlight the need to develop a potentially different approach, steer away from the anchor specific intrusive SI, more like a ground model based SI approach that allows the understanding of ground profiles and geo constraints without an intrusive SI at every single foundation location, which will cut costs while also being able to lower ground risk to an acceptable level. So now I'm going to talk a bit about the MA17 project itself, which is titled Site Investigation and Anchoring for Floating Offshore Wind, and this was delivered in part with ORE Catapult. So this project came about after the Floating Offshore Wind Centre of Excellence, which is a consortium of industry recognised companies established to drive the commercialisation of floating offshore wind. So they reviewed seabed conditions in the UK continental shelf and identified that floating offshore wind covers a huge area of the seabed, which has variable geology and geological conditions and geohazards that need assessing. There's also a large number of SI locations involved, because current best practice means you have to do an SI location at every single anchor location. And as I mentioned previously, that leads to a high number of SI locations potentially is required, which also leads to high site investigation costs. So therefore they recognise that there needs to be some research into how we can make SI methods more efficient but also balancing ground risk against cost. So the scope of the MA17 project involved creating conceptual models for 5 sites, hypothetical sites in around UK waters. And these fed into developing SI strategies, and this informed the SI strategies. And then a cost risk assessment was then carried out for each of these SI strategies. So the conceptual ground models were created based off of pre-existing data such as geological maps and scientific literature. I've got some examples here. The LOL collection is a very powerful resource for journals regarding engineering geology. And also eModNet has a load of really good maps, European related, good seabed maps and geology maps that inform the conceptual ground model. And overall, this conceptual ground model is overall a very powerful tool in instantly being able to visualize what's going on a site. And it's easy to communicate this to your client rather than paragraphs of information that they can't take in. But obviously there are limitations in fact that it's conceptual. There's a high degree of uncertainty in that you're using sources from scientific literature and geological maps that may have uncertainty related to them. For example, this ground model was created using BGS geological maps, which are dated from the 1980s, using sparse geotechnical data points. So this might mean that the conceptual ground model is oversimplified and actually in the sea underneath the ground, the geology might be much more detailed and finer details might be missed, such as paleochannels. Also, this data is based in the 1980s, where the technology wasn't as good back then, so it might be poorer data quality or resolution. So it's worth highlighting that and appreciating the uncertainties. So now I'm going to talk a bit about 2 of the conceptual ground models that we developed for the sites and how they informed the SI strategies and ground risk versus cost. So this ground model is from the northern part of the central North Sea, which has a relatively low geological complexity. You can see there's a few geological formations, but mostly the lithology is clay. There's a few geohazards such as boulders and ice plough marks, but overall I'd say there's a relatively low geological heterogeneity here. And because of this, the SI could be considered on a site-wide basis, initially using a 3D geophysical survey with targeted acquisition in areas of complex geological heterogeneity where there's high risk of geohazards or lack of existing GI data. And therefore you're able to capture the geological ground conditions, the variation in them, whilst be it having a number of SI locations, lowering ground risk enough to an acceptable level, whilst also maintaining acceptable cost for the developer. In contrast, this ground model is based in kind of the central part of the central North Sea, and you can see immediately that there's a higher geological complexity in that there's a few more geological formations. You can see variation in the thickness of these geological formations, which is got high ground risk. You can see paleochannels that can be variable, they can have variable infill in them, which need to be captured. So therefore, because of this high geological complexity, SI would probably be considered on a more anchor specific basis, try and capture all this geological complexity. And this approach does conform to current certification requirements, but there will be a high cost associated with it. So in summary, floating offshore wind is the future. According to the Global Wind Energy Council, approximately 80% of the world's global offshore wind potential lies in water depths greater than 60 meters. So it has huge potential. However, there are currently challenges associated with them, potentially, such as large complexity in geology over the turbine anchor footprint, which need to be captured in some way during the site investigation, and also large numbers of individual foundations because of the large numbers of anchors that are needed to hold the floating offshore wind turbine in place. So both of these challenges might lead to quite high costs associated with the site investigation. So there needs to be SI approaches needs to be efficient in order to capture the in order to capture the geological conditions without intrusive SI at every single foundation location, which could be done using a site-wide ground model based approach. So firstly, using a 3D geophysical survey to get a site-wide picture of the ground conditions, but then targeted acquisition areas of geological complexity. The importance, conceptual ground models are very important for floating offshore wind, particularly because it's such a new and emerging technology. It's a good initial thing to do to be able to help model potential site investigation approaches, thinking about ground risk versus cost, and that's really good to inform the developer what their potential options could be and how much it may cost and how much it may reduce ground risk. And it also helps to feed into anchor selection. You might be able to kind of have a look at what anchor types might be suitable for a site at first look. But that's very key. Conceptual ground model is an initial first look. There's high uncertainty associated with conceptual ground models, and they must be recognised in that they are based off of data online and in scientific literature, which the data quality might be limited or maybe based off of sparse geotechnical data points. So that must be highlighted and caveated. Just want to say as well, off of this, as well as my day job, I'm fortunate enough to go on a lot of field trips, especially with so recently I went on a field trip with the Quaternary Research Association to North Wales, and someone said that the best geologist is the one that has seen the most rocks. I thought that was quite good, really pertinent. It really struck me that that's true. But yeah, that's it.
Again, I think we've got time for a quick question if anyone's got one. I had a very quick one,
Yeah.
which was, I guess, interested in relation for moving from conceptual models to reality. I know some of these areas now we're beginning to see actual data coming back out. Do you see the conceptual model holding, or how much do you think it's changing?
I think there will be a bit of budge, obviously, because you're collecting. So it's about refining the ground model. It's a good starting place, but once you get that real data come through from the geotechnical and geophysical campaigns, you can then refine the model further and see much more detail. Yes.
Thanks so much. So you can catch Millie in the library afterwards. We'll move on to Georgie Harbottle. Again, I've been asked just to remind everyone that we've got these workshops going on in the council room. I think there's the neurodiversity workshop ongoing at the moment. And then later on, we've got the Environment Agency drop-in, I think. But you can register for these outside in the lobby. But Georgie, over to you.
Hello, everybody. I'm conscious I've got the pre-lunch slots. My stomach is already rumbling, so I'm not going to dwell too much. And it's nice to see, actually, that some of the points that I was going to talk about have already been kind of echoed by the earlier speakers, which is good. Particularly subsea cables, Joe, which is nice to see subsea cables getting some love, because sometimes they're seen as the poor relation in particularly offshore wind development. So yeah, I'm going to talk about geoscience foundations for a low carbon future. So I always find it super interesting, particularly at these kind of events, to find out how people ended up doing what they're doing. I know when I graduated in 2018, I had never even heard of the job that I do now. So it just goes to show that, you know, in a short space of time, you can realised there's a lot more opportunities out there. The eagle-eyed amongst you might notice that I started off doing a law degree, so that was a mistake on my part. But thankfully I was lucky enough after a year of that to meet somebody who was studying geology at Aberdeen, and thought, wow, that sounds way more interesting, and would rather spend 40 years of my life doing that than doing law, which I think in hindsight was a wise decision. I then, similarly to Millie, I started my career onshore, doing contaminated land and sort of small scale development site investigations. No disrespect to anybody who does that, but that wasn't for me. It was quite a lot of abandoned car parks, and yeah, just wasn't where my interest was focused. So after jumping around a couple of times fairly early on in my career, I then got my kind of break in offshore geotech with a subsea trenching company called Deep Ocean, who then unfortunately went bust. But that led me to moving into consultancy as a kind of subsea cables sort of specialist. And then in 2023 moved into my current role, which is a geotechnical project engineer with SSE. And for anybody who's not familiar with SSE, they are an energy company, and they supply power to some areas of the UK, but they also develop offshore wind, onshore wind, hydro, lots of different technologies. So, as has already been said, really, just to reiterate that offshore wind has got a key role to play in achieving these net zero targets. The offshore wind industry at the moment, as I've been discussing with some of the other speakers, is not in as good a place as it was 2 years ago. And I think that's something that if you are sort of applying to jobs in the near future, something worth considering and trying to keep on top of the trends that are sort of happening in the industry, particularly for developers like SSE. We've had project delays and things like that that have meant that progress that was there a couple of years ago has slowed, but these things do happen, and you know, we need the energy, so the hope is and the thought is that will continue to pick up over the next couple of years. I was going to kind of throw this out there and sort of test knowledge, but it's kind of already been covered. So as to how geoscience underpins offshore wind development, and as you can see from that diagram there, it underpins everything really, right from site selection to detailed design, construction, and sort of ongoing maintenance. So my role at the moment has expanded from sort of my background in cables. I now deal with site investigations for turbines, for jacket structures that you can see there, monopile foundations, covers the cables, these very large offshore substation structures, all the way up to the transition joint bay there, the landfall location where the cable and the power comes onshore. So my kind of move to SSE really was quite a big learning curve for me, because of my background, my university career, any of that didn't really prepare me for a lot of this. So a lot of the learning that I've done has been on the job, and that's not necessarily a bad thing, I don't think. So the reason I say that cables sometimes get treated as a poor relation is because we don't have these great big huge structures that we're kind of designing and installing, and you can see sort of to scale there, that's a suction caisson foundation from the Seagreen offshore wind farm. But my role now covers managing ground risk for different projects across all aspects of an offshore wind development. So as I say, that covers data acquisition. So I'm responsible for outlining what data the project needs and when it needs it, how we acquire it. So that's things like doing surveys, that's a CPT, offshore CPT cone penetration testing frame there that we use, through then to working with consultancies and design kind of outfits to produce ground models like Millie touched on, and then taking those ground models through to the design of foundations or cables or routes or all those kind of things. And a key part of my role really now is that actually day to day I don't work with a lot of other geologists and geoscientists. I've got a team there that I work with and that support me if I've got questions or anything like that, but I work within a multidisciplinary, typically engineering team, but it's also my responsibility to speak to project managers and people in charge of financing and all those kind of things. So I think in terms of transferable skills that were touched on earlier, what's really good about that is that it means that I get to use my geological knowledge that I find really interesting, but then it's also the important part of that is somebody will say, okay, so what? So this is really interesting geologically. So what does that mean? What does that cost? Usually is the key thing. And what are the risks associated with that? Again, this has kind of been touched on, but just some from a day-to-day perspective, what my job kind of looks like. In some ways, and in some tasks, my job's a little sort of one step removed from directly dealing with the data. So it is nice to get a chance to actually get your head back in it, and look at some proper geological data. But a lot of it's around managing the timeframes for different engineering studies and that kind of thing. I've got a few examples of data because it's always nice to look at nice pictures. This is a slice through a cable corridor for a subsea cable. So you can see here, this is a kilometre point, KP 137. So 137 kilometres offshore is what we're looking at here, and this is a projection of the seabed surface. You'll notice the textures, so you've got some boulders, sand waves, that kind of thing. Apologies, there's no scale on here, but for example, that kind of sand wavy type structure there could be somewhere between 5 and 10 meters long, 5 and 10 meters high potentially. And then some of the other data that we would look at, this is actually for a floating site or potential floating site. So this is a slice through some of the seismic data, and you can see a really, really nice outline of a channel here, a huge channel. And again, the scale of this, that's 400 meters. So it just gives you an idea of the kind of size and scale of the data sets that we're dealing with. And again, I guess kind of following on from Millie's presentation, this is a slice through an interpreted ground model for one of our project sites. And it just shows you really that all these different blobs here are all different channel features, channels within channels, and just to give you an idea of the sort of complexities of the types of ground conditions that we're dealing with. And for example, you can imagine that the difference between trying to place a turbine here, for example, versus placing it here could have significant engineering implications. Subsea cables, again, has been touched on previously, and it's great to see. So, I really like subsea cables, but some other people find it boring. I spied this picture, which is a really good illustration, I think, of how significant subsea cables are. Again, before I got into this industry, I had no idea about it. Key for things like telecommunications, fibre optics, as well as the power cables and inter-array cables. Question, does anybody know, and this image is a clue, when the first telecoms cable was laid? Transatlantic telecoms cable. Oh, it's on there. Well spotted. Yeah, so that surprised me that it was in fact 1866. So yeah, it just goes to show how key these kind of things, this infrastructure is really. Was laid in the 1850s, so from west coast of Ireland to Newfoundland. And in terms of lifespan, the subsea cables that we're talking about are anticipated to last, or hope to last, for a design life of 25 to 30 years. So quite a significant period of time. I won't dwell on this because we've seen similar images, but in terms of scale, this is a cable drum. So these are inter-array cables, just to give you a sense of scale. So when the cable's laid, it's wrapped around these enormous drums, and this is a significantly bigger one. I think that's maybe an export or something. But yeah, just to give you an idea of, we're not talking about extension leads. It's significant in terms of scale. Why is cable protection important? So I'm talking about laying cables, but actually we need to bury them in most cases to protect them under the sea. But why is that significant? So if these cables do get damaged, it can cause, depending on what type of cable it is, it can cause major disruption to telecoms, to power supplies, to all those kind of things. And 2022, you might have heard that 2 telecoms cables were damaged off Shetland, and that caused the island to kind of go dark for several days. And they suspected that that was damaged by fishing operations. But obviously we've also heard things about sort of potential intentional damage and Russian interference and those kind of things. So it does become quite significant in terms of risk assessments and those kind of things. In terms of offshore wind, 80% of insurance claims in offshore wind are related to subsea cable failures. So that's a significant risk and a significant cost. And looking at average downtime of 40 to 60 days potentially for these repairs. And as you can imagine, subsea cables under this subsea and under the seafloor, it's not a simple operation to fix. So what damages subsea cables? So I'm not convinced that that's real, but I like that image, so I left it in. Shark bites, apparently it does happen, but it's not a key consideration. Sediment mobility, so sand waves and things moving across the seafloor can result in buried cables being exposed, obviously then putting them at more risk for things like fishing gear to strike them, or anchors and those kind of things. They can also get over buried in the same way, and that can damage the cable through restricting the heat dissipation from them. Things like seismic activity, landslides, probably more significant for other areas of the world, but still a consideration. And I've touched on fishing, so there's certain types of fishing gear that, depending on how they're positioned on the seabed, can impact subsea cables, and obviously that's quite a tricky interface to manage sometimes, in terms of how we balance the need for the cable infrastructure with the need for fishermen to be able to access the seafloor. Another key one, and increasingly so really, is the threat from shipping. So ships, as you can see here, is a kind of vessel density map showing ship traffic for the North Sea. So you can see that shipping traffic typically follows fairly uniform patterns, and there are sort of designations and things to tell particularly the larger ships where they need to go. But accidents happen, emergencies happen, and what they call errant anchoring, or anchoring in an emergency, can happen. And in that case, rather than dropping anchor in a designated part of the ocean where there's no infrastructure, it might be that an anchor gets dropped and unfortunately it lands on top of your cable or your pipeline. And when I'm talking about anchors, I'm talking about something the size and scale of this, if not bigger, for these huge cargo ships that seem to be getting bigger and bigger. And so the resulting damage can look something like that, potentially, which is a catastrophic failure. So as mentioned about how cables are laid, there's loads of videos on YouTube if you want to look at these. It is pretty cool. This is part of the job that I found really interesting. That's the big cable drum on the back there. It's now kind of lying down, but the cable comes over the back, drops over the back of the vessel, and then is laid on the seafloor. And then this image here, for certain types of cable lay, depending on the ground conditions, this is using a cable plough. So here the cable's getting laid at the same time as the plough is actually like an onshore field plough. Ploughs the cable into the seabed to depths of somewhere between 2 and 4 meters potentially, depending on the ground. That's a better picture, but some of these machines can be enormous. Like there's people there, but that's a fairly small one. You also get things like this, which is a jet trencher. So this is like a big power wash nozzle effectively on the back. Does a similar thing, and it creates this trench that the cable gets laid into, but it does it by just blasting out the sediment. So again, it's key, like geoscience assessments for this is key, because if you're using it in the wrong kind of ground conditions, you're not going to achieve the burials that you set out to achieve. This one's a mechanical one, so it's a bit like a big chainsaw on the back of it that sort of chews through rock. Again, there's some really cool videos that explain that a lot better than I have on YouTube and things like that. And yeah, that was it. That's a picture of me for scale, and that's one of these big, I think that was a multi-tool, so it did different things, jetting and sorts of that they were showing off and showing the capabilities of it, and they actually did an onshore demonstration, which was pretty cool. But yeah, any questions, catch up with me.
How are cables compared if they're damaged like that?
Have we got time for it? No. I will answer that at lunchtime.
Thanks, Georgie. Thanks so much for all the speakers. That ends that session, and I'll pass over to George to say what's happening.
Given the overrun, we're just going to roll straight into session 3. So I'm going to invite John back to